So until now, we have completed the study regarding the Lagrangian mechanics and Hamiltonian mechanics. The remaining pieces are regarding the rigid body motion, normal modes, and vibrating string that will be treated in terms of the Lagrangian density function, and we also derived the wave equations. So remaining part will be closely related to the bridge onto the quantum mechanics. In this chapter is the basis for the matrix algebra. We studied diagonalization. In this section, in order to develop a theory for diagonalization of a Hermitian matrix, we study the orthogonality of the eigenvectors of Hermitian matrices. Hermitian matrices are that appears in quantum mechanics. It has, in the case of real matrix, it is a symmetric real that is closely related to the orthogonal matrix. And in the complex space, the transpose and complex conjugate that represents the Hermitian conjugate, and the Hermitian matrix is the same as the Hermitian conjugate matrix. In that case, the eigenvalue of the Hermitian matrix is always real, and all of the eigenvectors are orthogonal, including multiplicities. By constructing the orthonormal relation among the n linearly independent eigenvectors, it is straightforward to construct a theory to diagonalize a matrix. Once we can diagonalize a matrix, the algebra becomes very compact, and the structure of a mechanical system is revealed trivially. Okay, before we study that, we first consider the tensor analysis. Tensor is an extension of a vector. We recall that the rotational transformation of a vector can be expressed in terms of this expression. The component, ith component of a vector after rotation can be obtained by summing index j, here j1, after multiplying the matrix to the original vector. The rank of a Cartesian tensor, here we consider only the Cartesian tensor because the rotation matrix is very compact in the Cartesian coordinate system. So as far as the tensor analysis is concerned, the rotation this transformation matrix is written in the Cartesian coordinates instead of the general curvilinear coordinates. So the transformation rule for a vector is given in here, and Cartesian tensor has n vector indices, and here n is the number of indices as well as the rank of the Cartesian tensor. So the vector is a Cartesian tensor of rank 1, and we have an object without vector index that is called the scalar. The scalar is a Cartesian tensor of rank 0. So Cartesian tensor of rank n has n vector indices, and for each vector index we multiply rotation matrix R. we'll find that the rank 2 Cartesian tensor is a kind of matrix, and the simplest rank 2 Cartesian tensor is Kronecker delta. And actually the Kronecker delta is invariant under rotation. Let's see. This is a Cartesian tensor of rank 2. The Kronecker delta is in here. If I introduce new coordinates after rotation, we have original rank 2 Cartesian tensor delta AB, and A is connected to this A, and it is transformed into vector index I in this rank 2 Cartesian tensor after rotation. Index B is linked to J through rotation matrix R. So every vector index has a connection to the final vector resultant vector index linked by multiplication of rotation matrix. Alright, so we organize the order because each vector is just a scalar. This is just a number. It commutes. We have RIA, delta AB, RJB. AA are connected in order, BB are connected out of order. We need to replace the order. Exchange this order. That means that by transpose. This is transpose, then this two indices is exchanged. And now correct connection of repeated indices achieved. Therefore, we have a product of three matrices, R identity and R transpose. The final vector indices will be I and J. Because our identity does not change this, and we find that R transpose. The basic property of the rotation matrix R is orthogonal. That means the transpose is the inverse. Therefore, this is identity. Identity's ij element is called the Kronecker delta. So Kronecker delta is invariant on the rotation. And this is the only rank 2 tensor that is invariant on the rotation. Let us find some examples of tensors, especially vector. We are familiar with the rank 1 tensor, that is vector. Let us consider the rank 2 Cartesian tensors. As a simplest Cartesian tensor of rank 2, we consider inertia tensor. That can be defined through the orbital angular momentum of a rotating object. An object that has the lever arm x with respect to the origin and respect to the rotational axis n hat, and it is rotating. We consider the case it rotates about the n hat by the angular velocity omega. So n hat omega will be vector omega. If the lever arm is fixed to the rotational axis, in that case orbital angular momentum, that is defined by the x cross p, can be computed easily. The momentum p will be the mass times velocity, and if we apply the Rodriguez formula for rotation, we find that the velocity of the object mass will be omega cross x. Therefore, if we substitute this one in here and apply the triple vector product formula back cap rule. Back means the middle one. Omega is factored out. Back, BAC, A dot C will be x squared, that is r squared, lever arm squared, minus cap. C means x vector in here. Cap, AB, it is x dot omega, will be appearing in here. Here, r squared is a lever arm squared, the x vector squared. The ith component of the orbital angular momentum can be written in the form the ith component of omega and given vectors. Here r is replaced with the xk squared, where k is summed over. And ith component of the second term will be minus xi, and this is scalar product, so we use different dummy vector index j to express this in terms xj omega j. Now omega I can be written in a different form, delta ij multiplied by omega j. In that case, we have omega j's can be factored out. So if we factor out this, if we pull out this factor omega j, then in the brackets we have delta ij xk squared minus xi xj. Now it is written in the form matrix I multiplied by column vector omega, so where j is summed over, where the matrix I has a ij element of m delta ij xk squared, where k is summed over, minus xi xj. We have two vector indices in each term. Therefore, this matrix is a rank 2 Cartesian tensor. In a similar manner, in the multiple expansion of a charge distribution, the leading contribution for the potential will be the monopole. Monopole piece will be just charge over radius, and dipole structure is dipole, electric dipole dot x over r square style, and the next series, next contribution, the multiple expansion appears quadratic dipole moment. There's a quadruple, electric quadruple contribution. Electric quadruple contribution has this vector, and this vector has a very similar structure with a delta ij style and xi xj style. This is called the electric quadruple moment, and this is also our Cartesian tensor of rank 2. So analysis of tensor analysis quite important, especially in the rank 2 Cartesian tensor. As far as the rank 2 Cartesian tensor is concerned, you must master this relation. In summary, on the rotation, for each vector index, rotation matrix should be multiplied in front, because any vector in here is assumed to be expressed as a column vector. So on the rotation, rank 1 Cartesian tensor, that is a vector, is transformed into Vi, and the index is connected to the original index, vector index, through the rotation matrix. Rank 2 Cartesian tensor has two vector indices, and for each index, we multiply the rotation matrix on the left. And A is summed over, A is transformed into the new vector index I, B is transformed into new vector index J to find this component. In case we have three vector indices, multiplication of rotation matrix should be made by 3 times for each vector index. And in the case of n vector index case, which is the rank n Cartesian tensor, every vector index has a connection to the new vector index with the rotation matrix. We just have seen that Kronecker delta is a rank 2 Cartesian tensor, and this rank 2 Cartesian tensor has a special property that after rotation the structure is identical to the original form. So the Kronecker delta is the rank 2 Cartesian tensor which is invariant under rotation. We can also consider a rotational invariant tensor of rank 3. Leviticus tensor is a number that depends on the 3 vector indices. If ijk's are even permutation, for example, ijk is 1, 2, 3, 2, 3, 1, 3, 1, 2, they are even, and odd permutation 2, 1, 3, 3, 2, 1, 1, 3, 2. There are 6 cases that has non-vanishing value for Leviticus tensor. For even permutation, epsilon ijk is a +1. For odd permutations, epsilon ijk is -1. And among 27 cases, there are 3 even and 3 odd cases. So remaining 21 cases, all the tensor values are the same as 0. So let us consider the rotation of this Cartesian tensor of rank 3. As we have already explained, each vector index has a rotation matrix to be connected to the final resultant tensor after rotation. So A is connected to I through Rij, and B is connected to J through Rjb, and C is connected to K through Rkc, where A, B, C are all summed over. So let us first consider epsilon prime 1 to 3. Epsilon prime 1 to 3 is epsilon prime 1, 2, 3. So R1A, R2B, R2C, epsilon ABC. Right? This is actually the determinant. Right? A, B, C. So this is first row, second row, and third row. Choose A. A is 1 among 1, 2, 3. B among 1, 2, 3. C among 1, 2, 3. And then multiplied by the epsilon ij, epsilon ABC, and times 1. 1 we can conventionally choose 1, 2, 3. So we are interested in the value of the determinant R. And we have determinant of R. What's that? Determinant of R transpose. This should be the same as determinant of R. Determinant of identity is 1. Alright, we have R transpose is R inverse, which is R transpose 1. That is orthogonal matrix property. Therefore, R transpose R determinant is identity determinant of 1, and this is 1. As we know, this is product determinant R transpose determinant of R. Now, if I apply this, it is the determinant of R's squared. This is 1. That means the determinant of R is either plus 1 or minus 1. Plus 1 is the proper rotation. And this is a proper rotation multiplied by a kind of flip. And this one has a kind of parity transformation. So as far as a pure proper rotational transformation, we have plus 1. So first, if determinant of R equals 1, then epsilon prime equals epsilon 1, 2, 3. If determinant R is minus 1, improper rotation, that is 1, 2, 3 prime equals minus epsilon 1, 2, 3. This is not invariant, but as far as this determinant R is satisfied, epsilon prime 1, 2, 3 is the same as epsilon 1, 2, 3. And after that, we can make a permutation to find out the 6 other contributions, and 6 other contribution has the same relative sign. So everything is proved. So as far as the proper rotation is concerned, epsilon ijk is invariant under rotation. And if the determinant R is minus 1, it is not invariant, but it is just the opposite side. Let us solve the linear equation of n variable, n unknowns from x1 to xn can be written in the form. Here, the coefficients shows that in the first index of the coefficient means the nth equation in this order, and the second index of the coefficient represents, that is multiplied to the nth variable, nth unknown. We can rewrite this one as a matrix form, and the coefficients are collected to construct an n by n matrix. And unknowns from x1 to xn can be collected into a single column vector, and right hand side can be collected into a single vector, single column vector b. All right. Then this matrix equation becomes matrix A times x equals b. A is the n by n matrix, x is the single column matrix with n elements, and b is a single column matrix, that is a column matrix with the n elements. The solution to this equation is x equals A inverse b, as far as the A is invertible. That means the determinant is a non-zero. If the determinant is 0, that means among n linear equations, at least one equation is linearly dependent on the others. Therefore, the determinant of A must be non-zero to have the inverse matrix. If there is an inverse matrix, then the dimension of the system is preserved. Next, we consider this identity matrix is a diagonal matrix whose elements are all 1. Especially the first column is a unit matrix 1, 0, 0, 0. The second column is the unit matrix with the elements 0, 1, 0, 0, 0. In the same manner, the last one is a unit vector with the components all zeros except for the last component, which is 1. Let us make use of this kind of abbreviation. A matrix can be written as a list of column vectors. The first one is the first column, A1. A2 represents the second column of this A, and AN represents the nth column of this matrix. In that case, the identity matrix can be written as the first column is E1, second column is E2, and nth column is the unit vector En. We know that A times A inverse is identity matrix, because identity matrix can be expressed in terms of unit column vectors. We write in this way. Again, the ith column of the unit matrix is the unit column vector EI. Again, A times A inverse ith column will be EI. Because, and here A inverse I means ith column. That is EI. Okay? Because of this. And this is the identity's ith column. In summary, if X is invertible, the solution for this equation will be X equals A inverse B. Alright, recall that if I have a product of two square matrices, AB ij element of A ij can be obtained by multiplying the ith row of matrix A and jth column of matrix B. Therefore, the jth column of matrix AB can be obtained by multiplying A to the jth column of matrix B. If I want to read the ith row of A times B, then what I have to do is multiply the ith row of A to the matrix B. Alright. Next, let us introduce this kind of representation. This one is the same as the identity matrix, except that the ith, I equals 1, here I equals 1, ith column of this matrix identity with X. Therefore, because identity matrix is E1 to En, this one, first column replace with X. That means first one will replace with X. And the E2, En. Okay. If I replace the first column, E1, with X, then X is a column vector with the unknowns. That is X1, X2, and Xn. If I take the determinant, the multiplication of this contribution is this one multiplied by this determinant. This is another identity matrix, and this is just 1. So x1 times 1 equals this one's determinant is x1. And if I replace this one with the ith element, then ith one is replaced. Therefore, diagonal element will be xi. So the answer is xi. The reason why the remaining pieces are vanishing is if I multiply x2, I have to choose the elements in the remaining pieces. And every element must have 0. All of the elements are 0. 3, if I choose 3, everything should be multiplied at least once. So everything is 0. So all the other contribution must vanish. Therefore, if I replace the ith component, ith column of the unit vector with x column vector, then the matrix has the determinant of xi. Then if I collect everything together, then I have the answer. That means xi, okay, in summary, identity 1x is replaced, second column is replaced with x, third column is replaced with x, and the nth column is replaced with x. Therefore, determinant of this matrix is x1, this one is x2, the first one is x1, this one is x2, and so on, to find that this is determinant, this determinant is xn. Now we have a second. We have A inverse A is identity, which is the list of unit column vectors. What happens to the ith column of this matrix? Ith column of this matrix is just A inverse multiplied the ith column is a matrix A. And ith column of this matrix is EI. Therefore, let me write it in this way. A inverse A is identity. That is a list of xn's. Okay? And then, because this is this, A inverse multiplied by first column is A1, A2, and AN. All right. So this is the answer, but let me summarize everything all together. AX, okay, this is x1 to xn that we are interested in. And This one is A inverse times B. A inverse times B. Let us write it. We recall that xi is the determinant of identity matrix with the ith column replaced with x. Now we substitute everything. E1 is A inverse times A1. E2 is A inverse times A2, and so on. And then x is A inverse times B. Therefore, every element has the factor of A inverse matrix multiplied by a column matrix. For E1, it is multiplied by the first column of A, E2 multiplied by the second column of A, and X is A inverse multiplied by B. That means if I factor this A inverse out, this right side will be A matrix A, except that the ith column is replaced with the column vector B. Therefore, this matrix can be written in this form: A inverse times matrix A, except that the ith column is replaced with B. Now, it became a determinant of a product. Determinant of a product is a product of determinant. So A inverse is factored out as a separate determinant, and this part will give the determinant of this. And we know that determinant of inverse is inverse reciprocal of the determinant. Therefore, our final result is determinant of a matrix A with the ith column replaced with B divided by the determinant of the original matrix. If I collect everything all together into a single column vector, we have over factor of 1 over determinant of A, and first element will be determinant of A with the first column replaced with B, second column replaced with B, and nth column replaced with B. This is Cramer's rule for inverse calculation. Let us extend this method. What happens to the case when the matrix, this column vector B is replaced with the identity matrix? That means identity matrix is a list of unit column vectors, right? And here X is A inverse times identity. So X is actually the inverse matrix. So the previous result can be applied to obtain the inverse of this matrix. As we know, X can be expressed in a compact form as a list of column vectors. Then, the equation shows that the ith column of this is A times ith column of X matrix. And right side ith column is EI. Therefore, this is AXI equals EI is the same as AX is B. The only thing is I replace this unknown with ith column of the matrix X and replace with EI. Therefore, I can replace this X will be the ith column, and this here B is to be replaced with the EI, and everything else will be identical. As a result, we recall that single column equation This one is from A1 to AN. That means ith column is replaced with B. But now ith column of this inverse matrix is to be replaced with EI. Therefore, the ith column of inverse matrix is 1 over determinant of A, and ith column has the replacement of the unit column vector EI. And the replacement of what column? Here number of rows will be determined by the column of matrix A to be replaced. Therefore, in summary, we list everything all together. This I is the first column, that means I is 1. This I is 1 and I is n. Alright? And this is the number of rows. This first row has the first column replacement. Nth row is nth column replacement. This is the final result. And in general, if I pull out the ij element, and this one determines I, this one determines I. So ith column of matrix A is replaced with, this is a jth column, E means a jth column, E is index. So this EJ. Alright. So let us compute the inverse matrix of this. Determinant of A is 1, 4, minus 6, that's minus 2. And what we have to do is to find out these matrices. One element, so 1 1 1 2 2 1 2 2. Okay, first we find out this one. The first column is replaced with E1. Copy the second column 2 4. First column 1 3 is replaced with E1. There's a 1 0. Then the determinant is 1 4 minus 0. So 4 is the determinant. 1 2 element 1 2. The first column is replaced with E2. First column is replaced with E2 0 1. And the second column is invariant. Determinant 0 minus 2 equals minus 2. 2 1 element, this second column is replaced with E1. Second column is replaced with E1. And first column is copied in here. Determinant is minus 3. 2 2. Second column is replaced with E2. Second column is replaced with E2. And first column is invariant. And determinant is 1 minus 0 is 1. If I copy these four numbers in the right places, 1 1 1 2 2 1 2 2, and then multiply the reciprocal of the determinant, that is minus 2, I have this result. This is the answer. We can check elementary computation for general 2 by 2 matrix inverse. Matrix A is A, B, C, D. It is trivial to compute the determinant of A, that is AD minus BC. Now let us compute the first column is replaced with E1. First column is replaced with E1, 1, 0. And the second column is invariant. First column is replaced with E2. AC is replaced with 0, 1. And BD are copied. 2, 1. Second column is replaced with E1. That is 1, 0. A, C's are copies. And 2, 2, second column is replaced with E2, and A, C's are copied. Now let us compute each determinant. This is a D, and this is minus B, and this is minus C, and this is A. So copy those elements in the right place, 1, 1, 1, 2, 2, 1, 2, 2, D, minus B, minus C, A. And over factor is the reciprocal of the determinant. There's a 1 over AD minus BC. Alright. Next, we consider the eigenvalue problem. So eigenvalue problem appears in quantum mechanics frequently, but it also appears in the classical mechanics. In classical mechanics, for example, in the rigid body, the inertia tensor is real and symmetric. Usually is a rather complicated form with 9 components. But because it is a real and symmetric, they have only 6 linearly independent elements. The 6 linearly independent elements are to be transformed into only 3 elements if I choose the very simple axis that are called the principal axis. The principal axis for a rigid body system means the eigenvectors of the system, and the principal. If we choose the principal axis to be the x, y, z axis, they are all perpendicular to each other, then the expression will be very compact, and only 3 elements that are diagonal elements survive. In general, the connection to our principal axis system to a general system is connected by a rotation. And that triple rotation that is usually parameterized by Euler angles. Anyway, the eigenvalue problem also appears in the classical mechanics as well as the quantum mechanics. And if we consider the operator, matrix representation of the operator, or that we can also directly deal with the operator. And as far as that operator is a Hermitian or real symmetric, the eigenvalues of that operator are all real. And in addition, if the two states have different eigenvalues, they are orthogonal. Even in the case of multiplicity, the double roots can appear for the eigenvalues. We can always find a distinct eigenvector with multiplicities, so that the number of linearly independent eigenvectors for n degrees of freedom must be n, and the eigenvalues are real. Then it is possible to find a system whose coordinates are just coordinates for the eigenvectors are just unit vector, trivial unit vectors, 1, 0, 0, 0, 0, 1, 0, 0, 0, and 0, 0, 0, 1, something like that. If we find that frame, if we find a kind of unitary transformation from our matrix representation to another matrix representation, then the matrix is diagonalized. So once the matrix diagonalized, the form of the matrix and the form of the eigenvectors are very, very compact. the transformation from the complicated matrix representation system to a compact system, we shall find that the transformation is a unitary, and it is very simple. The complex conjugate and transpose of the matrix, of the transformation matrix, will be the inverse of the matrix. In the case of a real coefficient, real element matrix, it will be an orthogonal matrix. The transformation is orthogonal if the elements are real. In the case of complex, it should be the unitary matrix. Okay. The eigenfunction, we call this eigenfunction and this eigenvalue. And if the operator is a Hermitian, we shall find that the eigenvalues are all real. For example, alright, so Schrödinger equation, this is a kind of eigenvalue equation. And this Schrödinger equation is a linear second order differential equation. So if I have some solution that is up into here, because the derivative operators are linear, this is a linear operator. And this relation gives the solution for the eigenvalue problem. That is, the eigenvectors, they construct the basis of the Hilbert space of the system. Let us consider the eigenvalue problem in the matrix form. Identity can be multiplied to rewrite this one. Then if I move to the left-hand side, this becomes a very simple linear equation. If there exists a determinant, if the determinant of this one is non-zero, then this matrix is invertible. If it is invertible, I can multiply the inverse matrix to find that x is exactly 0. If x is exactly 0, that is called the trivial solution. Well, I'm not interested in a trivial solution that does not deal with any physics. Instead, we are interested in a non-trivial solution that is non-zero. In order to have a non-trivial solution, this one must not be invertible. Therefore, the determinant of this one must be 0. We say this is a circular equation of characteristic equation. In general, matrix A has the elements of complex numbers. Therefore, this determinant, this n by 1 matrix, square matrix, has the nth order equation for lambda. The fundamental theorem of algebra states that there are complex and complex solutions for this eigenvalue lambda with multiplicities. That means, for example, x squared equals lambda squared equals 0 is 0. We have a single solution, but that is not a single solution, but two solutions, where doubly degenerate case. So with multiplicities, in principle there should be n solutions for the eigenvalues, and in general that eigenvalues are real. But we should find that if the matrix A is Hermitian, that eigenvalues are all real. Okay, we can find that inverse matrix has a common eigenvalue, common eigenvector, but the eigenvalues is 1 over lambda. So you can follow in a trivial way. The next one, we consider the simple problem. We already know it is very simple. The eigenvectors will be 1, 0, and the other one is 0, 1. If I try this, you will find eigenvalues 1 minus 1 plus 2. However, if we follow the rule, a minus lambda 1 is 1 minus lambda, 2 minus lambda. Its a determinant is this one, to find that lambda equals 1 or 2. Substitute 1 in here, you find 0, 0, 0, 1. Suppose that AB is this AB, column vector AB is the eigenvector. Multiply here, you will find that this is 0. The multiplication, the result is 0b. Therefore, from this, it is b must be 0 for this eigenvalue. In general, lambda equals 1 eigenvector is a kind of form A0. And in the case of lambda equals 2, what we find is minus 1, 0. The result multiplication gives a minus A0. Here, it should be 0 because the eigenvalue equation, therefore A equals 0. That means a kind of 0b style is the eigenvector. What we are interested in is a unit eigenvector. The value square of this is normalized to be 1. In that case, our final answer is 1, 0 for the eigenvalue lambda equals 1. 0, 1 for eigenvalue lambda equals 2. If the eigenvector is complex, then we can consider the normalization. First, what we need to do is take the Hermitian conjugate. Hermitian conjugate means the transpose and complex conjugate. Transpose is 1i, and then we take the complex conjugate to find 1 minus i here. If we multiply these two, our normalization is 2. So we define vector x with the square root of by dividing the square root of this normalization. We find that 1 over square root to 1i will be the normalized eigenvector. Next, we consider two eigenvalue equations. Suppose that alpha is the eigenvalue of eigenvector x, beta is the eigenvalue of the eigenvector y. We multiply y dagger to the left-hand side of the above equation, and we take the Hermitian conjugate of the second equation. That's y dagger, a dagger. We know that multiplication of the matrix or operator, transpose is like that, reversed. Complex conjugate is like that, and Hermitian conjugate is transpose after transpose we applied complex conjugate, so a b dagger is a b dagger a dagger. So therefore we obtain this. Because beta is a number, complex number, after Hermitian conjugate, after taking the Hermitian conjugate, beta becomes a beta star. Now we multiply x to the right on the second equation. If we list them, we find that. However, A is assumed to be a Hermitian matrix. Hermitian conjugate is itself. Therefore, left-hand sides are identical to each other. If we subtract, we'll find 0. The right side is factorized with alpha minus beta star multiplied by y dagger x. Suppose that we have a single one, I mean x and y are the same, the eigenvalues are the same. eigenvectors are the same. If the eigenvectors are the same, then the eigenvalue must be the same. Therefore, what we find is first x dagger x, and because eigenvectors are the same, this eigenvalue must be the same. So we have alpha minus alpha star. But if I square this eigenvector, because we are considering the non-trivial eigenvector only, the square must be positive definite. Because it's positive definite, alpha must be equal to alpha star. That means as long as matrix A is a Hermitian matrix, the eigenvalue is real. Because eigenvalue is real, I can replace this beta star with the beta. So for alpha minus beta multiplied y dagger x equals 0. If the eigenvalues are different, that means the states are orthogonal. It is 0. So as a result, we can construct this relation, orthonormal relation, after normalization. Every eigenvector is linearly independent of the other one, and the projection onto projection of the two eigenvectors are vanishing and survives only if the two are identical to each other. Even though there are some multiplicities, we can always find the orthogonal matrix, orthogonal contribution. For example, suppose this trivial matrix. This is identity matrix. The circular equation states that eigenvalues are degenerate, only a single eigenvalue. If I substitute lambda equals 1, circular equation becomes this. Therefore, this eigenvector, I have arbitrary value. That can be a linear combination of these two numbers, these two trivial vectors, 1, 0, elementary 1, 0, 1, or this kind of representation is also possible. We are free to choose the basis. So, anyway, because this matrix, this matrix has complete degrees of freedom, the dimension is not lost at all. Instead, even though the eigenvalues are identical to each other, or for example, the n by n matrix, n by n identity matrix, we have nth order multiplicity, so the n degeneracy. Even in that case, we can always find the orthogonal eigenvectors. Therefore, in summary, if A dagger is A, is a Hermitian, these eigenvalues are all real. If eigenvalues are different, they are orthogonal. Even though they are degenerate, in case of degenerate, we can always find the orthogonal eigenvector. The detailed proof is given on this page and next page, and it is straightforward to follow. So I advise you to follow those computations. And regardless of the multiplicity, we can always construct the orthonormal condition for the normalized eigenkets. The normalized eigenkets has a scalar product with delta ij, where I and j runs from 1 to n. That means, just like a linear algebra, the space generated by these spaces vectors is called the Hilbert space, and this one represents any state that is described by the system. So we are able to expand any state satisfying our condition in terms of various eigenvectors, which is basis vector. As long as we write the matrix representation of these eigenvectors to be unit form, then the matrix A is completely diagonalized, and coefficient of each projection onto the ith state, ith eigenvector, can be obtained in this way by making use of the orthogonality condition. All right. So let us consider the completeness relation. The direct product of psi I and psi I dagger summed over the index is actually the identity. This is because this is the complete set. This one, psi I, the eigenvectors, a set of this set of eigenvectors is a basis of the Hilbert space we are considering. The simple example is given here. Consider 2 by 2 complex matrix. So we have psi 1 and psi 2 to be the two linearly independent and orthogonal and the normalized states. So it is trivial to find that psi I dagger, psi j is delta ij, right? So let us check if it is true. This is called the completeness relation. Psi I direct product psi I dagger is the first component 1 times 1 direct product 1. It's 1 is 1 0. It's Hermitian conjugate is 1 0. The first row is obtained by multiplying this number to this row. So 1 0. Second row is obtained by multiplying this number to this. So 0 0. 2 2 is, this is 2 psi 2. This is a psi 2 dagger, and first row is obtained by multiplying this number in here, 0 0. Second row is obtained by multiplying this number to here, that is 0 1. If I add these two matrices, what I find is identity matrix. This is correct. Okay. The second one, even though it is not this simple form, we can also consider orthogonal matrix that also satisfy this orthogonality relation. All right, psi 1 times psi 1 dagger. Psi 1 is here. Sure, we have 2 square root of 2, so we have 1/2, 1 1, and Hermitian conjugate. First row is obtained by multiplying 1 to this row, 1 1, and the second row is same. Second, psi 2 cross psi 2. Psi 2 here, psi 2 here. Minus 1 1, Hermitian conjugate minus 1 1. First row is obtained by minus 1, multiplying minus 1 to this one. 1 minus 1. Multiply 1 to this row. That is a minus 1 1. Although each part has a non-vanishing off-diagonal elements, if I add these two up, what we find, off-diagonal elements all vanishes and diagonal elements becomes identical to 1. That is identity matrix. So if you have found a complete set of basis vectors that are the eigenvectors of you have identified all of the eigenvectors of the system, the eigenvalue equation, and if you have normalized the eigenvectors with unity, then what you will find is the direct product of eigenvector and its Hermitian conjugate summed over all n states, it becomes 1. And it is true only even for the case of n goes to infinity, is a countable infinity, it is true. Even it can be extended to the continuum limit, then the identity will become not a canonical delta function. This one will lead to the continuum limit by a Dirac delta function. Bracket notation is just simple compact form of this matrix algebra for the Hilbert space calculation. For column vector for the Hilbert space, we use psi, but instead we can also use a cat vector. If I introduce a Hermitian conjugate of a column vector, then Hermitian dagger, Hermitian conjugate, the bra can be used. There's a 1-to-1 correspondence. And the scalar product can be defined by psi dagger chi, and psi dagger chi can be expressed in the bracket notation. This is bra, psi bra, and this is chi cat. Direct product can be expressed as column vector multiplied by the row vector, right? And in the bracket notation, psi bra and psi cat. The completeness relation can be written in this form. The direct product of psi I and psi I dagger summed over all possible states is expressed in terms of bracket of same quantum state summed over all I states. That becomes, in either way, it is an identity operator that does not contribute to anything, that does not change anything. It is a complete projection. It is not collecting a single part or partial contribution. It is a complete contribution will be projected out if I apply this operator. For example, psi can be expressed as a cat notation, and identity operator can be applied to a cat notation. Identity is, according to the completeness relation, identity is a sum of bracket direct product. Bracket direct product can be multiplied, and this is a linear combination of ith eigenvector state with some coefficient. We remember this coefficient can be obtained by projecting out the ith component that is to be multiplied by the psi I component to this wave cat. So that is simply in the bracket notation I bra and the psi cat. So let us record a simple example for Pauli matrices, spin matrices, sigma 1, 2, 3 are written here. We know that it is traceless Hermitian, and eigenvalues of all three matrices are identical, and eigenvalues are the same, traces are the same, because they are related by similarity transformation. That means there is a unitary transformation that transforms these three matrices to a single one. And and that one can be obtained by solving the circular equations to find out the eigenvalues, identical eigenvalues. Once you know the eigenvalues, you can construct the eigenvectors and we normalize to make them unit normalization. Finally, you can find each eigenvectors. They are all orthogonal to each other. These are the orthonormal relations. And sigma 3 also have the form. But you will find that this form is a very simple one. And these two matrices can always be transformed by making use of the unitary transformation to arrive at a simple form that is a sigma 3. And this is we shall find that a kind of diagonalization process, you can transform this sigma 1 and sigma 2 into sigma 3. Thanks.